We're going to session 5, FPGA-based computing engines. I'm the session chair, Zhou from University of Pittsburgh ECE department. We're going to have 4 talks, and the first one and third one are videos because of the visa issues from the speaker. And the second one, the fourth one, will be in-person talk. So I'm going to introduce the first talk speaker, hAP, a spatial von Neumann heterogeneous automata processor with optimized resource and I/O overhead on FPGA. The speaker is Wang Xuan. Wang Xuan received his Bachelor of Science degree from School of Physics Science, University of Science and Technology of China, USTC, in 2018. He's currently pursuing a PhD degree in School of Computer Science at USTC. Thank you, Gabe.
Hello, I'm Xuan Wang from University of Science and Technology of China. It's a great honor to introduce our work to you. The title is hAP, a spatial von Neumann heterogeneous automata processor with optimized resource and I/O overhead on FPGA. This is the table of contents. First, I introduce the background, including the automata processors and some automata models. Then I propose some research challenges of AP. Then I introduce our approaches. Finally, we show our experimental results. In some applications, there is often a requirement to efficiently match some patterns on input strings. These patterns can be described by a regular expression set. In real applications, they are often large, containing thousands of regular expressions. Automaton is a classic computing model for regular expression matching, including NFA and DFA. They can run on CPU and GPU. However, the automata processors, also known as AP, based on FPGA and ASIC, can run automaton with lower power consumption and higher performance. NFA and DFA are two classic automata models. At one time, they can be multiple active states in a NFA, forming an active state set. DFA has only one active state at one time. For each input symbol, DFA only needs to access the memory once, so it has a higher performance. We can convert an NFA to DFA using the subset construction algorithm. However, DFA generally face the problem named state explosion. In real applications, it is almost impossible to use DFA due to the state explosion. In order to combine the advantages of NFA and DFA, researchers have proposed some semi-deterministic automata models, such as the hybrid FA, SFA, and GFA. Among them, hybrid FA consists of a head DFA and a tail NFA, where the head DFA is generated from a part of NFA, and the states that are point to explosion are excluded from it, which is called the tail NFA. Now I introduce the architecture of AP. The architecture of AP is divided into 2 parts, kernel and reporter. The kernel is responsible for running the automaton model. The reporter is connected behind the kernel and is responsible for collecting the activation information of the report states. According to the architecture used by the kernel, APs are divided into spatial APs and von Neumann APs. On the von Neumann APs, a DFA state transition can be completed within a fixed 1 clock cycle, so it can achieve high performance. However, because of the DFA state explosion, the von Neumann AP is unable to handle large regular expression sets. Researchers have proposed Spatial AP, which uses the fine-grained parallelism of logic circuits to process NFA. However, on FPGA, the Spatial AP mainly uses logic resources and cannot efficiently use the on-chip memory resources. This causes them to face the problem of LUT resource shortage. Instead, although the von Neumann AP cannot fit large regular expression sets, we notice that the unit resource overhead is significantly smaller, which means that if we replace Spatial AP with von Neumann APs while avoiding state explosion, we can optimize the resource overhead. Now we introduce the AP's reporter. Each report states in the automaton corresponds to one output bit. Since the automaton in real applications has thousands of report states, the AP needs to output a bit vector with thousands of bit wide. Therefore, usually AP reporter will compress the output report. We divide the compression approaches to two categories. The first category is dynamic report compression, which compress the report vectors using their sparsity and can achieve a higher compression ratio in average. However, its compression ratio is unstable. It is because in a local short term, the NFA may generate a large number of dense reports and leads to a local congestion, local I/O congestion. In practice, this will reduce the performance. The second category is static report compression. It analyzes the NFA model and gives a static compression scheme, so the compression ratio is stable and not be affected by any factors at runtime. However, the current-only static compression approach, DRM, cannot achieve a high compression ratio. Now I introduce our proposed approaches, starting with the flex hybrid FA, a better hybrid FA generation approach. The original hybrid FA generation approach has some problems. First, it's sometimes too conservative. Secondly, it is sometimes too aggressive. Last, it is not flexible. It cannot adjust the size between head DFA and tail NFA. We summarize the reason for these shortcomings as the original hybrid FA is not a quantitative approach. As a result, it is not helpful for us to get valuable heterogeneous AP. We found that the key to generating a good hybrid FA is to select the most appropriate states to add to the tail NFA. Here we show an inspiration. In this example, we want to pick an NFA state to exclude from DFA and add to tail NFA. We have two options Q3 and Q5. Q3 only appears once in the DFA, so if we choose Q3, the size of head DFA can only be reduced by 1. Q5 appears 2 times in the DFA, so if we choose Q5, the size of head DFA can be reduced by 2. To sum up, the most frequent NFA state in all DFA states is the most critical, and the best choice is to move this state to tail NFA. Based on this, we propose a suboptimal quantitative hybrid FA generation algorithm called flex hybrid FA. It let head DFA grows gradually from the initial state. For example, now the NFA states in the rectangle has been added to head DFA. Then we make a trio step, drawing their successor states to the head DFA. Then we use the approach we just proposed to find out the most critical states from head DFA and include them until the head DFA satisfied a constraint. The head DFA size divided by its NFA size must be less than lambda. This constraint will be used to trade off in our architecture design. Then we do these steps repeatedly until we cannot no longer add any state to head DFA. We can finally get a hybrid FA. Then I introduce our proposed static report compression approach. As an inspiration, we first propose an optimal static report compression approach. Let's illustrate it with an example. On the left is an NFA and corresponding DFA. Then we list all the report states of DFA. Next, remove the NFA non-report states from it. Only keep the report states. The combined sets, the obtained sets has 6 elements, and each element is a possible combination of NFA report states. We called it the report state combination set, SF. Then we binary encode each item in SF. Obviously, 6 elements need 3 bits to encode. By now, we have compressed the report from 4 bits to 3 bits. Note that this is a static compression because the encoding rules are pre-analyzed before the runtime. Moreover, this is an optimal static report compression approach. In other words, we cannot find a static report compression with a higher compression ratio than this approach. However, it is unrealistic for real applications because it needs to build an entire DFA with an unfeasible time overhead. To this end, we further propose an approach that is equivalent to this optimal approach. We called it high-efficient automata report compression, HEARC for short. First, it analyzes the exclusion relationship between all NFA report states. Getting an exclusion matrix, for example, it can be seen that Q5 and Q3 are exclusive and Q5 and Q4 are not exclusive. The way to analyze whether 2 states are exclusive is to get a minimum NFA that contains the 2 states and then use it to build a small DFA. With the exclusion matrix, the second step is incremental generate report states combinations, SF. Initially, let SF be an empty set. Then consider the NFA state Q3. Since Q3 may be activate alone, we add the set of Q3 to SF. Then consider the NFA state Q4. Q4 and the pre-existing Q3 form a new set Q3 Q4. However, according to the exclusion matrix, Q3 and Q4 are exclusive, so the set of Q3 Q4 does not need to join SF. Then consider the NFA state Q5. Q5 and the pre-existing sets in SF will form 2 new sets, namely Q3 Q5 and Q4 Q5. According to the exclusion matrix, Q3 and Q5 are exclusive, so the set of Q3 Q5 does not need to join SF. Then Q4 and Q5 are not exclusive, so the set of Q4 Q5 needs to join SF. By By analogy, finally, we get SF with 6 elements, which is the same as the result of the optimized static report compression approach. We can prove that the HE-arc algorithm is significantly faster than the optimized static report compression. The practical result has indeed confirmed this. In this NFA, the optimized static report compression takes several hours, but HE-arc only takes a few seconds. Next, we introduce our architecture design. We propose hAP, the spatial von Neumann heterogeneous AP. It contains a von Neumann architecture for head DFA, a spatial architecture for tail NFA, and a HE-arc-based reporter. In the part of von Neumann architecture, we designed a data path that is as streamlined as possible, which can support several DFA compression techniques, including alphabet reduction, ADFA, and majority transitions. By doing this, we reduce the resource overhead to 44 bits BRAM per DFA states. The part of spatial architecture has an average resource overhead of 0.8 LUTs per NFA state. In the reporter, we use the pipeline design. Each pipeline state encodes 128 encodings to ensure that it does not constitute a bottleneck of clock frequency. Note that our proposed flex hybrid FA provides a user constraint, lambda. If we adjust lambda, the resource overhead of hAP is as shown as this curve. The pure spatial architecture corresponds to the blue triangle in the lower left, which uses a large number of LUTs but does not use BRAM. As lambda increases, the von Neumann parts increase, which will use more BRAM and less LUT. According to the resource configuration of specific FPGA, we can control lambda so that the resource usage always falls at a worthy point. For Xilinx FPGAs, we set lambda to 1.6. For deployment, we write a deployment framework in Python. It inputs a regular expression set. Then it runs flex hybrid FA and HE-arc algorithm. Finally, it generates the Verilog HDL of hAP. At runtime, the FPGA inputs a string and output compressed reports. Now we introduce our experimental results. We choose the large regular expression sets in animal zoo as benchmarks. Their NFA states is from 40,000 to 100,000. First, we run the original hybrid FA generation and our flex hybrid FA generation on same benchmarks. The results show that flex hybrid FA can generate significantly smaller head DFA and smaller tail NFA. Then, we evaluate the advantages that flex hybrid FA bring to hAP. We compare our hAP's kernel to the previous resource-optimized AP kernel, Reaper Plus. The left figure is the results of Reaper Plus, which uses a lot of LUT. The right figure is the results of our hAP. It can relieve the pressure of LUT by 1.7 to 10 times. Then we evaluate the HE-arc report compression algorithm. we compare its compression ratio with the previous SOTA dynamic and static report compression, the results show that HEARC can get a significantly higher compression ratio. As a static report compression approach, HEARC brings another advantage to reduce the resource overhead of AP reporter. This is because it only needs to encode according to the pre-analyzed encoding table, while dynamic report compression needs to schedule and cache the report vectors on chip. Finally, we show the overall comparison, including AP kernel and AP reporter. It can be seen that our work can significantly save resource overhead, which brings benefits of reducing power consumption by 4 times to 6.6 times, and for the first time supports the deployment of large automata or small-scale FPGAs. Second, since HEARC achieves a stable and sufficient high compression ratio, our work can achieve a higher performance. To summarize our work, our direct contribution are 2 new automata algorithms and the heterogeneous AP based on them. In addition, our work also brings some inspiration. First, we provide a new perspective for the design of AP kernel. That is, it is not necessarily limited to pure NFA and DFA. The semi-deterministic models may bring better results. Second, we show the power of the static report compression. Finally, we found that HEARC algorithm can analyze the combinations of certain state subset in NFA, which may be used in other fields. For example, if we can model a circuit system, a multi-core system, or a cluster as an NFA, then this analytical approach may guide resource sharing among the units. Our work is open sourced here. Thank you for listening.